Hello friends, this is an update video regarding my GPS tracker design VALTRACK version 2, and this is a second revision of the design. As you can see, the second version is having a nano SIM card adapter. I have left out some of the pins on a 2.54 mm header. Using these connectors, you can drive a relay or you can also control a siren to alert in emergency purposes. To give you a brief idea on what components are present on the board, this is the nano SIM card adapter as I had said, and this is the EEPROM chip, and this is the accelerometer, and this is the MCU STM32L051 series. It's a low power series which is very useful in conserving some power. This is the 3.0 volts regulator. The SIM800 module only supports 2.8 volt IO levels, so I used a 3 volt regulator instead of a 3.3 volts. 3 volt IO lines will be supported without any problem. And this is a transistor driver, and on the other side we had changed the battery charger chip from a TI part to a monolithic part. So this chip is manufactured by Monolithic Power Systems, and this can take in 12 volts as well as 5 volts to charge the internal battery and as well as supply to the system. So the GSM module and the GPS remain the same, and we also reduced the size of the inductor to a 4020 part, and the SOS switch remains the same. And there are 3 LEDs for indication. This is the LED which is controlled by the MCU, and these 2 LEDs are controlled by the battery charger chip. And there is one more LED which is the network LED which I have not assembled. This will be controlled by the GSM module to indicate whether the signal is available or not. And this is the 12 volt connector input. You can connect the vehicle battery directly to this input. This is the ground and this is the positive line, and there is also USB connector available if you want to use the device as a personal tracker, and you can charge the internal battery using the USB connector also. And for the antenna, we have provided a UFL connector here. So using this connector, you can connect any of the standard GSM antennas available, and otherwise you can just use a wire like this shown in this board, and it will work just fine. And this is the internal battery connector. You can connect a 3.7 volt or a single cell lithium ion battery here. It can also support lithium polymer batteries also without any problems. And the main important additions in this design are the 2 Mosfet power switches which we have used to cut off the power to the GPS or the GSM modules entirely. So these are the 2 power switches which we have used. These 2 power switches drive the power to the GSM and the GPS modules, and you can control the enable lines of these power switches to completely disable the power to the GSM or the GPS, which is very helpful when you are limited on battery power and you want to save some energy. And one more update is that after seeing the videos I had posted on VALTRACK V2, I got a requirement for customizing this design to design a GPS tracker which will run for 1 year on a single battery charge. So I used the same design, ripped off the accelerometer, the battery charger and all the Mosfet drivers, and the device will directly run on a lithium ion battery pack, and it will send only 1 packet daily in the morning at 9 AM. So that design I made and shipped to Lithuania, and that design is working perfectly. So this device can also be used for the same purpose. If you have any similar kind of long interval applications, then you can use the Mosfet power switches present on the board to control the power to the GSM and the GPS devices, and you can put the microcontroller also in sleep mode, and you can only wake up whenever there is an RTC alarm and send the device update and again switch off the devices. The boot time of the GSM module is around 30 to 35 seconds. So once you turn on the GSM modules or give power to it, it takes around 30 to 35 seconds to wake up and connect to the network. And the GPS module, if you are outside or outdoors, you will get the GPS signal instantly in around 10 to 15 seconds. I have also exposed the microphone connector and the speaker connectors, and I have also left out the I2C lines on this board, which will be helpful if you want to integrate any other sensors onto the board. They are just SMD pads left out like test points, but if you want, you can use it for experimentation. On the connector side, I have left out 2 connectors for relays. So you can control 1 ignition cutoff relay and you can control 1 siren using it. And I have also left out an analog input which is connected to the ADC pin of the microcontroller, and you can easily measure analog voltages present at this pin. And I have also left out a digital input which can be used to detect high or low signals by the microcontroller. So it's just a digital input with a Mosfet in between, so you can connect even higher voltage signals like 12 volts also. So the microcontroller will detect it whether the power is present or not present. If you need to use any of these features, you need to have the correct pinout. I will share the pinout later. Don't just use what I had explained in this video. I just told it for demonstration. As I had promised in my previous video that I would be making a GPRS tracking demo also, I had been busy with developing the hardware for the next version. So now the GPRS tracking demo is ready. I was able to send data over MQTT to a MQTT broker called cloudmqtt.com, and I was also able to send GPS data by HTTP to a REST API endpoint provided by Dreamfactory. Now I'll show you how the device is able to send data to a REST API endpoint and also to a subscriber via MQTT protocol. I have developed a demo firmware which will be able to show us the device capabilities by switching to MQTT demo to HTTP demo to SMS tracking demo also. Now let us insert the SIM card into the device and connect 12-volt input to it. So as soon as I give power, the red LED starts glowing. This LED I should remove because as long as the power is present, this will be turned on by the battery charger, indicating that the power is good. If we want to save some power, we need to remove this LED and use the microcontroller to detect the status of the charger being present or not. Now, as I had said, the device can be programmed using the USB connector because the SWD lines are exposed on this connector. Let's connect the USB connector, and so this is the ST-Link debugger I am using. The SWD lines are coming from the ST-Link to my board through the USB connector. Open the code, compile and debug. Now let us run it. The int1 variable will have the motion status, meaning if it's 1, there is no motion detected, and if it's 0, there is a motion detected. So as soon as the board starts, the GPS starts searching for the signal, and the GSM model starts initialization. So it will make some of the setups like setting the mic volumes and setting the GSM module to text mode. It will look for the signal strength, and now it will check whether the module is able to acquire the GSM signal or not. There is a variable called as int1 which will indicate the motion trigger status, meaning if it's 1, there is no motion detected, and if it's 0, there is a motion detected. So when I touch this device, the LED, motion LED, this is the LED which I am using as a motion indicator. So whenever I touch the device, the LED turns off, indicating that the motion was detected, and you can also observe the changes on the int1 variable. So it becomes 0, and it'll and the software automatically resets the accelerometer to go back to non-triggered state. And this is the GPS status variable, indicating that the GPS signal is not available. If it's B, it's not available. If it's A, then the GPS signal is available. And there is also a variable called as working mode. If the working mode variable is 0, then it's working in SMS tracking mode. So whenever you send an SMS to it, it will reply back. And if the working mode variable is set to 1, then it is working in TCP mode or MQTT mode. It will be sending data via MQTT to Cloud MQTT broker, and we can see the data on a Cloud MQTT subscriber here. So let me subscribe to the VALTRACK topic. If you have not seen my previous video on MQTT, I advise to see it so that you can understand what I'm doing here. So now we are subscribed to the topic VALTRACK on the cloudmqtt.com broker. Now the working mode is 2, meaning that the device is sending data via HTTP to Dreamfactory server. So it's using a REST API endpoint to push in the data. Now as you can see, the device is sending data at every 30 seconds. So 17 minutes, 30 seconds, then 18 minutes. Now there is also a variable called as motion alert mode, which will decide whether the device will send an SMS whenever there is a motion detected, or it will give you a call to the owner of the vehicle indicating that a motion was detected. So if it is 00, it will not send any alerts. If it's 1, it will send by SMS. If it's 2, it will send by a call. This is the ping intervals, means the device will send data every 30 seconds to the server, whether it is via MQTT or via HTTP. Now this is the Dreamfactory API where I'm seeing the data which is arriving from the device. So the device is sending data at every 30 seconds. So now if I change the ping interval to 10 seconds, now the device will start sending data every 10 seconds. Now as you can see, the device has started sending data every 10 seconds. The interval was changed dynamically from every 30 seconds to every 10 seconds. 10, 20, 30, 40. So now if I want to receive data using MQTT on the cloud MQTT broker, then I just need to change the working mode to 1. Now instead of sending the data via HTTP, it will start sending data via TCP. And the data will arrive on the subscriber. As you can see, I'm pushing JSON packets. So these are the packets that are arriving, and you can see the ping interval to set to 10 seconds. So as you can see, it has started from 2310, 2320, 2330, and the earlier data, which was up to 2300, has come here. So 2310 is on the TCP. We didn't lose any packets because the data is being put on a circular buffer which will save the data, and whenever we change the data transfer mechanism, it just takes and puts it onto the different channel, which is MQTT. So the device is sending the device ID, which is a unique identifier for each tracking device, and the date and the time, and it is also sending an event type, which is gping here. Now the device also sends other events like a reboot event. Whenever there is a reboot event detected, whenever there is a restart on the device, a reboot event is pushed onto the circular buffer, which is sent to the server. And whenever there is a motion detected, a motion event is triggered, which can be used to send push notifications from the servers to Android applications or mobile handsets. The ping interval is also present in every packet. As you can see, when I change the ping interval to 10 seconds, it is updated in each packet. There are also different variables, which is engine status. As I had said, there is a pin left out, which will be useful in detecting any digital inputs that can be connected to the engine status or the engine key. So it can be used to send the engine status also, whether it's on or off. And there is also VBAT pin. You can connect the analog input left out on the device connector, and you can use it to connect to the vehicle battery, and that and the vehicle battery voltage can be read by the microcontroller and sent in this packet, in this variable. You can send different queries. We have not yet implemented any queries. If there are any queries to be sent, the device will respond back in this query response variable. The device will also send the speed, current speed of the device, and the latitude and longitude. Now there is no GPS signal available, so the latitude and longitude values are 0, 0. I am just sending 8 whenever the latitude is 0. It is for a different purpose. I will explain it later. So that was the MQTT demo and the HTTP REST API demo of the VALTRACK version 2.1. And now I will show you how we can use the motion alert mode set to 1, and we will see if there is any thing sent. I will put back the working mode to 0. There is also a motion timer, so that it will not accept any new motion triggers if there is any motion detected within 120 seconds. I have set it to 120 seconds. You can change it to any value you want later. maybe I will develop an Android application for setting all these configurations so that the device can be easily configurable for different applications. I will change the motion timer value to higher value now. If I trigger a motion, now let us see what happens. An SMS was sent to my mobile phone indicating that the motion was detected. And since it has not got any signal, it will send the last known location. Now let us change the motion alert mode to 2 and see what happens. I will change the motion timer to a larger value so that a new motion trigger is accepted. Okay. Now as you can see, a call was generated to my number. So it is coming from my test SIM card. Even if you don't receive the call will be automatically disconnected after 30 seconds. You can observe it on the screen here. So what happened is, last time when I had kept the device in my vehicle, by mistake I had answered the call instead of disconnecting it. So call was continuously running for around 35 minutes. So that's why I have put a timer which will cut off the call after 30 seconds. Now let us again change back the working mode to 2 and let's see what happens. I'll remove the motion alert. And now let us start looking at the data here. So the last packet which arrived here was 2650, means the next packet which was supposed to arrive was 2700. So that packet was not sent because we disabled the working modes from MQTT and HTTP. So it was saved in the circular buffer. Now it will be sent via HTTP to the Dreamfactory again. The ping interval can be set to any value greater than 10 seconds because the HTTP connection needs at least 10-second intervals to send the data properly. Otherwise, the device will not be able to process the packets fast because this is running on a 2G networks and the packet delivery takes some time. So the realistic ping interval for the device would be 10 seconds on HTTP, and on the TCP you can set the value to a lower value also. It can easily send that. The ping interval can go as low as 5 seconds on the working mode 1 because it's continuously connected to a TCP socket via MQTT. So 3110 came here. Now as you can see, the device has started sending the packets. These are the earlier packets which were coming at 10-second intervals. And now let us wait for the new packets coming at 5-second intervals. As you can see, the data has started coming at every 5-second intervals, 10, 15, 20 like this. So you can go as low as 5 seconds on a MQTT connection because it's quite fast compared to the HTTP connection. So that was the demo of the new version of VALTRACK version 2. And if you have any doubts or questions, write me a mail at ravi@valetron.com. And if you want to receive more updates on the product development, subscribe to my YouTube channel, and you can also subscribe to my blog www.raviyp.com, and I'll make sure to keep you updated. Thank you for watching.